I'm going to do another implicit differentiation problem here. This is problem number 9 from section 4.8. Asks me to differentiate e to the xy power equals tangent of y. You'll notice I have both an x and a y in this problem. Not solved for y. It's not solved explicitly, or not set up explicitly. It's set up implicitly. So I'm going to use implicit differentiation. The derivative of e to a power is e to that power. Except I do have to remember to multiply by the derivative of the inside function. So when I start out, it's still going to be e to the xy, but I have to multiply by the derivative of the inside function. And this is where you have to be careful, because notice that xy is a product. Okay, so according to the product rule, I'm going to take the derivative of the first with respect to x, and that would be 1 dx dx times the second value, which is y, plus the derivative of the second. Well, the derivative of the second is y. I'm sorry, the derivative of y is 1 times the derivative of the inside function, which is dy dx, derivative of y with respect to x, times that first value, which is x. Okay? That is the derivative of the inside function. Now, get a little simplifying here, because that simplifies down to 1. And that's equal to, on the other side, derivative of tangent of y is secant squared of y times the derivative of the inside function. Got to remember that chain rule. Derivative of y with respect to x, of course, is dy dx. Now, a lot of simplifying needs to happen here. I'm going to go ahead and distribute. So I just have a y here, and this is going to be multiplied, that's going to be multiplied. It's going to be y e to the xy when I multiply through, plus x e to the xy times dy dx equals, on the other side, secant squared y times dy dx. Now I can do a little bit more simplifying here. The big thing, I need to isolate dy dx. There are two dy dx's here. Always check. If you've got y's showing up in multiple places in your equation, you should have a dy dx showing up in multiple places in your equation. So, I need to go a little bit farther here. I'm going to get the dy dx's on the same side of the equation. Looks like it's going to be a little bit easier if I take this value over to the right side of the equation, since I only have that one dy dx over on the right side. Notice everything's a product here, everything's a product here, so I can just move that term by subtracting. And yes, I know it's kind of big, but how it goes sometimes. These are not like terms, so we get all kinds of stuff canceling and simplifying because of the subtraction, but there's not going to be much that I'm going to be able to simplify over on this side. I'm still going to have my secant squared y times dy dx. I'm going to have my minus x e to the xy times dy dx. Big thing here, notice I can factor out a dy dx from both of these values. Okay, that is huge. That's going to factor out in front. Of course, over on the left side, it's just going to stay the same as it already was. And I've got a secant squared y minus x e to the xy left over here. Okay, again, I want to isolate that dy dx. It's being multiplied by this entire quantity here. I have to divide by that quantity. And of course balance my equation by dividing by that on the other side. Okay, what's going to happen? Well, this divided by itself is equal to 1. So I have dy dx isolated on the right side of the equation. And on the left side, I have the oh so simple y e to the xy over secant squared y minus x e to the xy. And that's my final derivative, simplified as it may seem.